Imagine trying to land on the moon using nothing but candlelight math. In 1601, the most advanced astronomers in the world faced a problem so overwhelming it could take an entire lifetime to solve. The Emperor Rudolph II had ordered a perfected map of the heavens, the most accurate star and planetary tables ever created. The observations existed. The measurements were precise. But there was one brutal obstacle standing in the way of progress: arithmetic. Endless multiplication. Massive divisions. 7-digit numbers calculated by hand. One small error could destroy weeks of work. And this wasn't just slow, it was strangling science itself. Then something appeared that looked almost harmless: a table. 5,400 entries. Columns of numbers. But this table could compress months of calculation into days. It didn't look like a revolution, but it rewired science. Its name was Logarithms. To understand why this mattered, you have to step into a castle outside Prague and into the life of Johannes Kepler. Kepler was brilliant, intense, obsessive. He believed the universe had a hidden harmony, a mathematical order placed there by design. But belief wasn't enough. He needed data. And only one man on Earth possessed measurements precise enough to test his ideas: Tycho Brahe. Tycho was a nobleman, legendary for his precision, famous for losing his nose in a duel and wearing a metal prosthetic. For 20 years, he had gathered planetary data more accurate than anyone before him, and he guarded it like treasure. When Kepler arrived, Tycho didn't welcome him warmly. Instead, he gave him a challenge: solve Mars. Mars was chaos in the sky. It looped backward. It sped up. It slowed down. It refused to behave. Kepler arrogantly claimed he could solve it in 8 days. 8 days turned into a year. Then more. Because solving Mars wasn't about ideas anymore, it was about computation. Kepler guessed orbital parameters, ran massive arithmetic chains, checked against Tycho's measurements, revised and repeated. Over 70 times. And he made constant arithmetic mistakes. Imagine recalculating entire planetary models because of one wrong digit written by candlelight. That was the reality of early science. Not a lack of imagination, but a lack of computational power. This is the part history rarely talks about. In the early 1600s, arithmetic was the bottleneck of discovery. Scientists could imagine bold theories, but calculations consumed months. The universe was waiting, but the math was too slow. Meanwhile, others were circling the same idea. Could multiplication somehow be turned into addition? A geometric progression hinted at it. If you list powers of numbers, the exponents add when you multiply. Elegant. But impractical for real-world messy numbers like 41.8 multiplied by 740. The spacing between values grew too large. Precision collapsed. The tool wasn't scalable. Back in Prague, Kepler and Tycho convinced Emperor Rudolph II to fund a monumental project: the Rudolphine tables, star charts so accurate they would redefine navigation and astronomy. But 2 months later, Tycho fell ill and died. On his deathbed, he begged Kepler to finish the work. 2 days later, Kepler was appointed imperial mathematician. The burden was his alone. And it would take 22 years. Quick pause. If you enjoy stories about the hidden ideas that quietly shaped the modern world, subscribe. This channel is built for the breakthroughs history class usually skips. Kepler pressed on. He found a near-perfect planetary model, except it missed Tycho's data by 8 minutes of arc 8 minutes. A quarter of the moon's width. Most would have ignored it. Kepler refused. Those 8 minutes forced him to abandon the ancient belief in circular orbits. After years of more brutal calculations, he discovered the truth. Planets move in ellipses, not circles. And they sweep out equal areas in equal times. 2 simple laws, born from 8 years of numerical torture. But Kepler still needed computational acceleration. Around this time, a brilliant mechanic named Jost Bürgi created improved numerical tables using ratios close to 1, bringing numbers closer together for precision. It was powerful but limited in spread. And then, far to the north in Scotland, a man often mistaken for a sorcerer was building something even more revolutionary. John Napier understood the astronomer's nightmare. Endless calculation. He imagined motion along two lines, one slowing proportionally, one constant, and showed that multiplying ratios could correspond to adding distances. A continuous mapping. It was conceptually centuries ahead of its time. He called his invention logarithms. In 1614, after nearly 20 years of work, Napier published his tables, 5,400 entries tailored specifically to astronomers and navigators. And crucially, he made them public. Freely available. The East India Company immediately saw the advantage and distributed English translations to navigators. The age of the logarithm began. When Kepler received Napier's tables around 1617, it was a revelation. Not just because they sped up computation, but because they revealed patterns. When Kepler compared orbital periods and distances using logarithms, the relationship became linear.
Clean.
Visible. The square of the period is proportional to the cube of the semi-major axis. Kepler's third law. The harmony he had searched for his entire life appeared, and logarithms helped expose it. An English mathematician, Henry Briggs, later refined logarithms into base 10 form, making decimal shifts intuitive. For centuries afterward, log tables and slide rules became the computational backbone of science. Newton used them. Einstein used them. Oppenheimer used them. Engineers who designed early aircraft, skyscrapers, bridges, all depended on logarithmic computation. In 1972, handheld calculators replaced log tables. It seemed like the era had ended. But inside those calculators, algorithms still rooted in the same mathematical logic Napier and Briggs developed 350 years earlier. The invention didn't die. It became invisible. Logarithms were not glamorous. They didn't explode. They didn't glow. But they compressed human effort. They turned months into days. They allowed Kepler to decode planetary motion. They powered navigation, trade, physics, engineering, and eventually space travel. It's fair to say that the computational power of logarithms helped put a man on the moon. Here's the deeper lesson. The most powerful inventions aren't always loud. Sometimes they are infrastructure for thought itself. They remove friction. They amplify intelligence. They quietly multiply what humanity can do. So here's my question for you. What's the most powerful invention you've ever seen that looks boring on the surface? Drop it in the comments. I read them. And if you want a next story about the tool that replaced logarithm tables and quietly reshaped engineering forever, subscribe. Because the real revolutions are rarely obvious. They're usually hiding in plain sight.